Bueno, pues vamos a comenzar. Es el segundo seminario de esta serie que hemos llamado Seminarios de la Dirección y que están focalizados a fomentar cosas que estén en nuestro plan estratégico. Y como sabéis, en nuestro plan estratégico había un punto muy importante, que es ser capaz de que el instituto se mueva hacia cosas que estén inoperando o operando, ¿no? Es algo, yo creo que es un paso muy necesario y esto requiere también de un expertise muy sinérgico, puesto que suelen ser técnicas muy complejas, tecnologías diferentes a las que estamos acostumbrados y demás. Para mí, una de las acciones ahora que hay más interesantes en el panorama, digamos, de materiales es lo que está desarrollándose, bueno, un poco basado en la experiencia de Jordi Arbiol, y que es cómo combinar justamente un microscopio de alta resolución con un montón de otras técnicas que estén operando. Y esto se está llevando a cabo en ALBA y por eso le hemos dicho que venga hoy a contarnos lo que están haciendo, qué posibilidades hay y también deciros a vosotros que estéis abiertos para intentar colaborar o bueno, que nos cuentes cómo podemos estar ahí también de alguna manera, aunque estemos más lejos que tu centro de origen. Pues gracias por venir.
Gracias. Pues primero gracias por invitarme y poder estar aquí, porque una de las misiones de ALBA es que sea abierto para todos. O sea, al ser ICTS, pues veréis que hay la posibilidad de acceder mediante proposals totalmente abiertas. Además, son gratis, os pagan el viaje, podéis ir y jugar un poco con todos estos equipos. Yo venía a contaros un poco más la parte de TEM. También os contaré lo que queremos hacer conjuntamente con las... ¿En inglés o español? ¿Cómo? ¿Por qué? ¿Sí? ¿Español? ¿Está bien? ¿Sí? ¿Todos? ¿Sí? Vale. o English? No problem. ¿Sí? Okay. So, what I wanted to say is that this is an open, large infrastructure that is open to everybody. So you can apply for the proposals, they are open, and there is an external committee, not from ALBA, so we are nothing to do with that, and then your proposals will be evaluated, and depending on the mark that you get, you will have beam time and time in the microscopes, and you can combine both. You can go just for the microscopes, just for the beam lines, or both together. And also FIP is included, so you can also apply for FIP time in order to prepare lamella of your samples and then get some extra access. Of course, above all this, you also have collaboration, so you can contact any of us and then establish a collaboration, but think that this is open for everybody. So you will always have a technician that is expert on this type of techniques, and you can go yourselves and also do it. So this is completely open. So the idea today is presenting you the Joint Electron Microscopy Center at ALBA, and the main word here is joint. And it's joint because there are, you see, there are many logos here. It was impossible for ICN2, where I come from, to buy all this equipment. So we had to, for many years, talk together with many centers. CSIC is also included. ICMAP was one of the promoters of this project. And then all together could do it at the end, okay? So first, a small presentation about my group. I was here last year for the Nano series, and I was presented similar things, but today I will show you a little bit of research done with not with the equipment, because the equipment is just new, but the things that you will be able to do, or similar things with the equipment here. So my group is a group of microscopy, and then, of course, we are in ICN2. I was in ICMAP before, so we collaborate with different groups in different types of materials, and this is the usual part. So one thing that we like or we love is these nanowires and two-dimensional electron gases for quantum applications, and Ramon knows a lot about this. So we do a lot of microscopy in this sense. And then we work also in nanostructures for energy and catalysis, and the talk today will have a strong emphasis on this part. Then a little bit on oxides and ceramics as well, and then materials for bio. So graphene for, I don't know, implants for the brain, things like this. So there are groups also interested in this part of research. So this is where we are placed. You all know Barcelona. These are the Mediterranean shores. And here at the other side, we have the UAB campus, the Autónoma campus of Barcelona. And right here we have the ICN2 and ICMAP. They are close together. Most of you maybe have been there visiting some colleagues. And then at the other side here of the highway, you have, it's in the same campus, in the same UAV campus, you have the ALBA synchrotron. So this is how everything started. So one of the initial ideas of creating this, it was Xavier Obradors, the director of ICMAP. His idea was to have in UAV a microscopy center. So the first thing he did was trying to get good microscopists from around and create a group that was starting to promote all this. Then with the move to ICN2, Pablo Ordejon also was really pushing for all this. And then ALBA was super interested, because at the end, as you will see, there is a real move nowadays in the synchrotrons to have also electron microscopies next to them. And the reason is that in the past, you could see an electron microscope of, let's say, a photograph camera. So it was a camera to take pictures of nice structures, and that's all. But nowadays, with the high resolution you have, that it's going to picometers, and with the high energy resolution that it's going to milli-electron volts, like 5 to 10 milli-electron volt resolution, so you can do things comparable to the synchrotron with a much, much higher spatial resolution. So combining both things, this is what most of the synchrotrons in the world are now trying to do, creating this type of synergies for all the community to have all these machines put together, and then having the opportunity to interact with all this. So as you see, the first project was promoted mainly by ICN2, which the first microscope is, the ownership is from ICN2. At the end, someone had to have the ownership. ALBA is the center where we placed all the microscopes. And then ICMM-CSIC is one of the promoters as well. And you will see that IFAE, this is the Institute of High Energy Physics, and you will say, okay, they are not working really on materials, so what are they doing here? And this is for data analysis. So one of the most important things on all this is that you are generating tons of terabytes. And then what to do with that? You can have lots of PhD students to analyze all the data, but it's impossible. So at the end, what you need is really to automate all this using machine learning, deep learning, all this artificial intelligence enhanced, let's say, data analysis, and make real the part of analyzing all this big amount of data. So this is an important part that is there as well. And PIC, this is the Port of Investigación Científica. It's a kind of center of data, let's say, of big computers that is connected in the Spanish network of computing. And also, thanks to that, we have access to this, the type of computers we need to make this work. And of course, the UAV is also related to the project. So more or less, this is what we have there. The idea was, okay, which is the expertise we have? So we are good in electron microscopy. So the idea was to have the best that we could electron microscopes for material science. And then in the case of biosciences, we said, okay, you have the CNB here, which are the best in Spain and maybe one of the best in Europe on cryo microscopy. So we are not going to create a similar center because we have the experts here in Madrid. So the idea was to have a small cryo-TM to have the preliminary data that the groups that really have good data in this microscope can move to the CNB and then have the collaboration with them, which are the experts. So that was the idea. In the case of cryo, start from the basics. And in the case of material science, we had enough expertise to go to the, let's say, to the top. So here is how it was mounted. The microscope, it took several weeks, even a couple of months. And then this is the starting point of the microscope that was installed last December, so 2022. So last year, 2023, was the starting of the commissioning of the microscope, so testing and having several results. And this is the first microscope, the MEDCAM, which is now working, and it's working in full access now, because the first call for proposals was open last year, and the first users from everywhere in Spain, everywhere in Europe, could start applying last year, and they started in January. So now we have users from everywhere. The good thing is that as this is a microscope that was bought with FEDER funds, So we are keeping some of the time for the centers that were paying the feather, but ALBA wanted that to keep a lot of time also for the external users. And the idea is that ALBA is covering the cost of the microscope, so the ones that are applying for the proposals have completely free access, so you are not paying. And ALBA is also proposing that the ones that are coming from Spanish institutions, they will have the trip covered. So your trip is covered as well as for the beamline. So that's more or less the idea. And this is the microscope that now it's working. This is the one that we call the physical, or the one for physics, for quantum materials, etc. And the one for chemistry, in situ and operando, is the one that is coming next January. So this one, it's not already there because it took longer. And this is another project, it's a second project. And this microscope will be installed at the beginning of next year. But maybe this is the one that also it's very interesting in order to do this correlative microscopy between the synchrotron and the electron microscope. So this is the ICN2, and then the sample preparation lab is in ICN2. Why? Because from, I don't know, maybe 10 years ago when I was in ICMAP, what we did is we had no space in ICMAP, but we had many machines for sample preparation. But then in ICN2 they had space. So what we did is joining together. They were buying some equipment, we were buying some equipment, and installing this in ICN2. I was in ICMAP, so I was not in ICN2. Then I moved to ICN2, and we continued in the same relationship. So now, with the first project of the microscope, we could also buy a FIP, and it was from the same owners. So altogether, even UAB was collaborating to pay part of this FIP. So now all this equipment with also, let's say, a horsework microscope and then several SEMs, these are in collaboration, some with some other centers of research. And then this is the first project. As you see, it's a nightmare of logos because many people was contributing. Even we had sponsorship from BIST, which is the Barcelona Institute of Science and Technology, but also Microsoft was giving some money here to make this real. And then this is the first microscope for quantum physical sciences or material science for physics, also for chemistry, of course, but it's not for in situ, this one. And then characteristics is a double corrected microscope, can work in TM mode and STM mode. In both cases, you have 50 picometers resolution, more or less. In STEM, you can go down to 45, 40 picometers. Then a super EDX, which means that you have many detectors around the sample and you can detect all the EDX that are around. 4D STEM, which is this new technique in which you can calculate the momentum of the electron. So this is really funny. Before, you could only see the atomic columns in every material, but now you can even determine the momentum of the electron when it's crossing your sample, even in each atomic column. So you really know which is the deflection of your electron beam when you are crossing your certain atom or a certain column of atoms. And then what you can do is measuring the electric field or the magnetic field of the atom around. So it has been really, for example, in Complutense, there is Gabriel Sanchez Santolino. I don't know if you know about him. He has many works about this for the STEM in order to calculate magnetic fields and electric fields at atomic scale. So it's really, really nice what you can do with these machines. And then this Helios that is for the sample preparation. So this is all placed in ALBA. And then it comes the second project. This is the project that is inside this, you know that there is this Programa de Materiales Avanzados, which is, it's paid with next generation funds, and then every autonomous or community or region had to pay half of the other part. So Madrid, Comunidad de Madrid, is also participating here. So I think that several groups from ICMM are participating, no?
I think that is just for universities, in the case of the community.
Okay. Every community is totally different. So in our case, all the money, so we didn't want to fund groups because we thought that funding groups, it was just promoting the same, so we wanted to do something different and leave something for several years, so creating something that could benefit many other people. And so there are like 6, 7 different autonomous communities, Aragon, Valencia, Catalunya, País Vasco, Castilla-La Mancha, and Castilla-León. And then every community is distributing the money as in a different way. But in our case, what we wanted to do, so there are different types of materials of interest inside this. But what we wanted to do is this. So creating a platform inside the same joint electron microscopy center for multimodal, multi-length scale, and correlative in situ operando experiments. And what we wanted to do is combining all of these techniques. So scanning transmission electron microscopy, of course. We already had one microscope, and with this project, another one is coming. But then also scanning prof microscopies. I will show you which type of techniques they are implementing here. But the most important thing, and what makes this a little bit unique, it's the combination with the synchrotron X-rays. So what we want is going with one sample holder in the TM, have some experiment of catalysis with gas or liquid, electrocatalysis, photocatalysis if you want with gas, and then the same experiment, move the same sample holder, sometimes extracting the FIP or just with the same sample holder, introducing it in a certain beamline, and then obtain XRD, XAFs, or whatever you want. So this is what we are trying to do. We need to adapt. At the moment, there are 4 beamlines that we are trying to adapt in order to work with the same. And the first problem, in the microscope, you work with picometer resolution, but in the synchrotron, you have a beam that is like 30 micron. So sometimes the window that you have in the TM, it's too small for the synchrotron beam. And what we are doing now is adapting the beam lines, but also adding mirrors in order to focus the beam and make it at around 10 microns, less if we can, in order to get inside the window and not to detect the things that are around, okay? So this is the idea. We are working on this, and by next year, all this should be solved. So these are the partners of this project. And then I'm the scientific coordinator, and Caterina Vizcarri is the administrative coordinator. So we are really linked with ALBA in order to make this work. So these are the parts. I already told you which are the parts. But one of the most important things to make it work, as I told you, is the advanced infrastructure for data storage, data analysis, and data treatment. And this is key, because without this, we cannot do Operando. With Operando, you are getting online videos of all the processes, chemical processes that are occurring. And this is at atomic scale. So you are getting a lot of data, terabytes per hour. So what you need is really a lot of computers behind in order to get or to do something with all this data. And this is the microscope that the public tender is over now. So we could sign the contract before Christmas. And now we know that now we need to wait for 1 year in order to get the machine. But the microscope will be it's the most modern microscope that Thermo Fisher has at the moment. It's a Spectra Ultra. It can work for nearly 30 kilo electron volts to 300. So you can work at the energy of an SEM to the really high energy, 300 kilovolts. It's double corrected, monochromated, with all the different techniques you want. But it has a different issue. You could say, okay, this is similar to the other one. But no, this is really adapted for really in situ experiments. Because in this one, you can change the voltage as much as you want. You can go from 30 to 300, and in 2 minutes, work again without any difference in the calibration. So it's keeping the intensity in all the lenses while you are changing all your voltage. So that means that you can go from 30 to 300 in a moment and just continue working. With the other one, you need to wait for 1 day sometimes, waiting for the stability of the lenses. And another thing is the EDX spectrometer is super fast. It's at the moment is the world record in the, let's say, in capturing electrons, because it's the one that has the wider angle. And yeah, it's just amazing for detecting anything that is going on inside the nanocells, or the cells with liquids or even gases, and illuminating or whatever you want that happens inside. You can even apply bias while you are experimenting with your sample. So the idea is that we are going to buy, or we bought already, a sample holder for controlling a gas mixture, up to 3 different gases. Even with vapor, you can include vapor with 3 gases, and then control temperature and bias. So you can control the temperature of the sample, you can apply bias, and we can measure the gas that is going out from the reaction. So you know what you are putting in, but you also know what you are taking out, if the reaction is, if the process is okay, because the quantity of gas that you are producing is really tiny. So you have nanometer nanoparticles, so imagine what you can do, but it works. And then we also have bought an electrochemistry sample holder, so you can work with liquid inside, and for example, imitate a battery. Now it's really fashion to create batteries. So you have the electrodes, the counter electrodes, and you can create cycles inside, so you can test really your materials for batteries and see how it's going on with different types of electrolytes, etc. So many things are possible because you have the potentiostat and you can apply all these cycles. And you also have, or you can create these in situ electrodes with a FIP and put them inside, connecting them, etc. And another one that is very interesting, but this sample holder will not really work in this microscope because this is more for physics, and it's a cooling, heating, and biasing sample holder. Cooling to the liquid nitrogen, not helium in this case, but at liquid nitrogen we can study many phase transitions in superconductors, high temperature superconductors, but in many materials that are very interesting now, you can work at these cooling temperatures, which is better for plasmonics, phononics, etc. But also you can heat, so you can go from around 120, 130 Kelvin to 800 Kelvin. So it's really a wide range of temperatures, and you can also apply bias. So in anything you can create there some, I don't know, connection and see how your material is responding to the change of temperatures. And last but not the least is the application or the adaptation of the beamlines in order to be able to introduce your sample holder and measure exactly with X-rays inside the beamline. So different tests are now going on, and we hope to give you good news in the next weeks or months. So this is what we are doing now. So the project is ending next year in August, so we have still 1 year and a half, but the thing is it's quite promising at the moment. And this is the SPM platform. So apart or aside from the STMs, we are also, so this is the ALBA synchrotron. The Joint Electron Microscopy Center is here inside the ring, so it's in this site, more or less. So we are really close to the beamlines, so we are inside. So in the outer part of the ring, but inside the ring. So you can just need to cross the corridor and go to the beamlines with a sample holder. So we are 2 minutes from the beamlines. And then in this part, that was a wardroom, or I don't know how to call this. It was for old machines, I don't know, but now they are adapting this for the SPM platform. And the SPM platform, you know Carmen Ocal, and she is taking care of all the AFM, so she's from ICMAP, and with all these people, they are working on the part of AFM, and Aitor Mugarza from ICN2 is working on the part of STM. So the idea here is with the STM doing atomic manipulation, measure magnetic, ITS, Kondo, STS, etc., many things, vibrational, electronic, and atomic measurements. And then in the case of the AFM, they are trying to purchase the equipment to do nanolithography, magnetic, electrostatic, piezoelectric, electrical friction, chemical, so many, many things. There will be like 4 new equipment also dedicated to all this in situ part. And the good thing is that they also want to work with photon nanospectroscopies. So the idea is this tip-enhanced electrophotoluminescence inside the STM, and also here the tip-enhanced Raman. So this will be also possible with these new machines. And the best thing is also having the complementarity with the beamlines. So they are creating, or they are constructing or building, they already have some, but vacuum chambers in order to keep your sample for the AFM, STM, and then you can move the same sample with the same conditions to to the beamlines and then measure them in different type of beamlines. As you see, now one of these long beamlines has been approved, and this will be really interesting for all this project because we will be able to focus the beam at really tiny sizes and go to the nanometer, hundreds of nanometers, but to the nanometer scale, which is what it will be more comparable to what we want to do with the part of microscopies. And then also, they will work with different atmospherical pressures and also in temperatures from, in this case, from helium to 500 degrees. So it will be very interesting for batteries, electrophotocatalysis, optoelectronics, photovoltaics, etc. This part will be also open. So there will be options because ALBA, in all the machines they are installing, they want to keep a large proportion of time. In the case of the TMs, up to 60% will be open to everybody. So everybody can apply to that. And this means that everybody will have the opportunity to work with all these machines. In the case of the STMs and SPMs, sorry, STM and AFM, it's a little bit different because these need more expertise. So just a technician, it's not helping, so they will open it also, but for longer collaborations, I think. So this is something that is still on debate, because as far as I would like and ALBA would like, we want to keep it more open, but then everybody is like this. But the TM, which is the part that I'm coordinating, this will be almost fully open, so it can be open to everybody. And the main advantage of all this, it's the synergy with eDream. So eDream is the European network of electron microscopy, and ICN2, or I am one of the founders of this network, and then you see that most of the main electron microscopy centers in Europe are here represented, so there is one from every one of the large countries, but the best thing is that most of them have connections, direct connections with the synchrotrons. So ICN2 and GEMCA, which is this Joint Electron Microscopy Center, is joined with ALBA. CIMES and then ORSE are related to Soleil. The CNR in Italy, in Trieste, are connected to Electra, and also Oxford University is connected to Diamond. So this is the next step we want to go, and as you see, it's not something that we could do alone, but it's something that is the trend of all European. But the Americans are doing the same, and in Asia, they are trying to do the same. So the synchrotrons in Beijing, for example, they have also the part of microscopy attached or nearby. So that's the idea. And then the connection of eDream, it's also connected to ARIE, which is connecting all the different large infrastructures or networks of photons, lasers, ions, protons, high magnetic fields, neutrons, X-rays, etc. So here includes the network of synchrotrons, for example, of, I don't know, lasers, etc. And there's one of the centers here in Madrid as well. So these are large networks that we are in synergy. So that was the part of blah, blah, blah. Now let's explain some science, no? To show you what you can do with these things. And I will always like to show this atom. So the main idea, the final idea that we have with all these machines is looking at the atoms. No, this is an atom. And at the end, the main problem we have is that the atoms are not alone. Sometimes they are, but they are embedded in quantum dots now, very famous quantum dots. No, they won the Nobel Prize. So this quantum dot here, it's a pyramidal one. It has around 2,000 atoms. So the green atom is still there because I was painting in green, but if it was, I don't know, a dopant atom, it could be just embedded inside, and it's really difficult to be observed. But these quantum dots, sometimes they are not alone. They are embedded in different buffer layers and heterostructures like this, and now we have 200,000 atoms here. So in 200,000 atoms, my atom, the cation or the doping, I don't know, it's already there, but it's more difficult to be observed. And sometimes, like in Majoranas, when you want to create these larger structures, you have these, I don't know, nanowires with full of quantum dots and other several structures, 2D or two-dimensional quantum wells or whatever, but then the problem is that your atom is still there, the doping atom, but here you have billions of atoms. So the idea of these microscopies is scanning your sample, in our case with electrons, and going to the position of these atoms and make them shine somehow. So extract the information, even at the electronic scale. So you can get many information on the electronic state of your atoms or your layers in the material you are observing. So, sorry, in this case, this is the one, okay. So in this case, as I said, now there are new techniques in which you can scan your sample and not just detect the atomic columns, but also measure the momentum of the electron. So when your electron is crossing an atomic column, it's behaving depending on the electric field that it found. So depending on the interaction of this electron with your material, it will be deflected or not. And this is what you can measure with this kind of technique that it's called 4D STEM. So you are measuring the deflection of your electrons when crossing the sample. And with this, you can do ptychography, for example. But it's a really nice technique, not just to improve the resolution of your material, which I think the top resolution right now is 20 picometer in 1 TM, like the ones we have, by using this technique. But also you can detect electric fields, magnetic fields, even around atomic columns. So you can, for example, if you have gallium nitride, you can see the positive and negative charging field that is around every one of the atoms. The cation and the anion are creating small electric fields, and you can detect that. And you can see it, or you can map it. So you can go to the reciprocal space and get 3D diffraction maps in 3D and understand really the structures, but this can be done in a single nanoparticle. So you don't need anymore to go to XRD and get the whole material, because if the material is pure, that is amazing. You can detect in average what you have, but imagine you have a single nanoparticle, or maybe not a nanoparticle, but you have an inclusion inside your material. So you can go with your beam, go right there, and with a small tomography, you can get a 3D reconstruction of the structure of this small, I don't know, precipitate or a small nanoparticle. Things that we have done recently, you can map the bandgap of your material, and you can go with resolutions. Every pixel here is below 1 nanometer, so it's around 0.9, 0.8 nanometer every pixel. So the resolution here, it's showing the energy of the bandgap. So this is the scale here. So this is zinc telluride and zinc selenide. This is alumina. You know, alumina is an insulator. You have a really high, high bandgap, but you can measure it. But not just measure the energy. You can also determine if this bandgap is indirect, as the case of the alumina, or the direct bandgap in the case of these two semiconductors. But even more interesting, due to the strain that is going at the interface, you see that there is a phase transition from direct to indirect bandgap exactly at the interface, and this is due to the strain. So this is amazing, what you can really measure with the new techniques. Furthermore, you can obtain this type of 3D reconstructions and understand your material, because once you have these reconstructions, theoreticians can take these models and then try to get the properties of these materials when you know every atom where it is located, okay, the composition and etc. And moving to the nanomaterials for energy and environmental. So you can do many things: photocatalysis, electrocatalysis, batteries, photovoltaics, thermoelectrics, whatever you want. Every type of these reactions that you can imagine, you can do them inside the microscope. So the idea, going to this multimodal and multi-length scale, etc., is combining different techniques, because none of the techniques is perfect. I would say electron microscopy is perfect, but it's not. So everyone is lacking something. But then combining many of them, you can get information that you cannot get with just one of them. And this is the idea of a summary of works that I'm presenting it here for many years. This is, of course, not done in Barcelona yet, because we needed really good microscopes. So we were going around the world doing these experiments. But these are things that we will be able to do it here. So for example, this is a case in which we wanted to create This was done with, by one of my PhD students. And in this case, we wanted to create this single atom catalyst. In this case, she was thinking that maybe one of the atoms was not good enough. This was for CO2 reduction. And sometimes, as you know, there are many different steps in the reaction. So if you want to promote or improve all of them, one single atom is not working very well, because it can improve one of the steps, but then it not improve the others. So in that case, she wanted to combine iron and nickel, and even linking the iron with an oxygen. This was a kind of graphene-like structure, but with nitrogens surrounding the different ions that we had here for the metals. So the idea is testing first nickel alone, testing iron alone, and then testing what we call this nanoreactor with nickel and iron both together. So you see, in electron microscopy, we see here the kind of graphitic structure, this kind of structure with all the planes that look like graphite. But then we are at 2 nanometer scale, and every one of these single bright spots is a single atom. And this has to be, for sure, a metal, because the metal has a high Z number, high atomic number, so it's really bright compared to the carbon, nitrogen, and oxygen. So if every one of these spots, by the size and by the, let's say, brightness, it should be a metal atom, then with EDX, you can make a correspondence between what you are getting, if it is iron or nickel or oxygen or nitrogen, and more or less, you can see if there are couples together, like the ones that I'm circling here, when you can find one atom of nickel with one atom of iron. If you are a purist microscopist, you will say, I can believe that or not, because I need a double checking. This can be true, but can also be noise, okay? So I need a double checking. And for a double checking, if we use conventional techniques like XRD or like Raman, they are not enough. In XRD, what happens? This material, it's not really crystalline. We are not expecting clusters of iron and nickel. So we are expecting single atoms. Here we can see slightly the peaks of the graphite, graphene-like structure, but we cannot determine if these are really atoms of nickel and nickel and iron. So what we need to do is going to XPS, but even further, going to the synchrotron. And here, you can more or less determine the coordination of your atoms. Is it true? You see that all the peaks are not really adapting closer or exactly in the position that you are simulating. But if you combine this with the TM in which you are seeing the atoms, you can get an agreement in which more or less, not all of them, but most of the atoms will be in this position, okay? Getting this type of coordination and bonding. So then you can just go to the electrocatalytic performance of the sample. You measure the different samples with nickel alone, iron alone, or the combination of both, and you see that the combination is always performing better at the voltages that you wanted. So the stability is even much better in the case of using this combination of two. So this was just an example. So it's a lot of electrochemistry, but the idea is that combining these characterization techniques, none of them alone can give you the final result, but combining all of them, you have many clues that what you are experimenting, what you really have there, is what you could then simulate and extract if the energies of every one of these steps in order to go to the CO2 reduction is getting the lower energy, etc., which is the part that theoreticians are helping here, in order to understand if the mechanism is the one that you were thinking before attending to the process of the catalysis. So this is one of the works. We can go to another one which is similar. In this case, it's exactly the same. So here you have the single atoms. In this case, it was just iron. But here, again, combining it with synchrotron, in this case was not in ALBA, this was in Beijing. So that was done in another synchrotron. But now, if you have the microscopes and and the synchrotron right there, you will be able to do exactly the same in the same place. So that is the advantage of having all of this together. Or you can go to this type of catalysis. This is an example of how the microscopist can help the guys that are doing the electrocatalysis in this case, but how to combine the electron microscopy that allows you to create the models, the atomic models, with the guys that can simulate these models. So you will see how combining the electron microscopy with DFT simulations, you can get the answer to the mechanism that you are looking for. So in this case, is a reaction of hydrogen evolution. So what we want is to use this material. This is a publication from 2020, so it's a long ago. But the idea is you can use this material, molybdenum disulfide, in order to do a good hydrogen evolution reaction, but then you realize that this material is not working at all. So the idea of molybdenum disulfide is that you have a sandwich. You have sulfur, molybdenum, and sulfur. So the material, the basal plane of molybdenum disulfide, it's quite inert. It's not working, because the real catalysis would be done by the different molybdenums with dangling bonds. You need something to be attached to the, in this case, to the water molecules and destroy them and try to separate the hydrogen from the oxygen. But this is not possible with the basal plane of molybdenum disulfide. So the idea in this work was creating many grain boundaries, because at the grain boundary, you see that the coordination of the atoms is not the same as in the basal planes. You have many defects, and these defects create a lot of dangling bonds, which are really avid for the molecules of water. So what they will be waiting is for the molecule of water to separate it and break it. So that was the main idea here. With the TM, what you can do is analyze that and see exactly which kind of defect you have, and by the simulation and the model, you can determine which would be the catalytic site that would be active in every one of the cases. So you just need to create the models of this, in this case for the grain boundaries, and also different models for the edges of the material, because the edges are really reactive as well. So you can get the different types of edges that you have in your material, and then you can get the simulations here. You can calculate the hydrogen absorption free energy, and then what you see is that the grain boundaries are working much better, or the energy in order to break the water molecule is much, much lower in the case of the grain boundaries, this case of grain boundary, than the basal plane, that, as you see, is really huge. You need a lot of energy. If you only work with molybdenum disulfide with a perfect basal plane, the 001, it's really, you need a lot of energy in comparison to this type, for example, of grain boundaries. So what you can do is just, in this case, create this cell here, and with these windows, what you are doing is trying to measure the electrocatalysis only inside the window, because it's protected, all the rest. And the nice idea is that you can measure one grain boundary, one single grain boundary. You can measure one single edge, or you can measure the basal plane. Or you can go to one of these multi-grain boundary materials, like this one, and also measure it. And then the electrocatalysis is giving you that in the case of the multiple grain boundaries, you have the highest intensity, and the basal plane is really not working at all. But also here, the Tafel slope or the onset potential are the lowest are for these nanograins, which are the ones that are giving a better catalysis. But at the end, in order to understand that, it's good to simulate, but in order to simulate, you need to know the structure. And the only way to get the structure is getting these nice pictures in the electron microscopy, and then, of course, understand the material and create the models. So moving further, okay, now we have this multimodal. We can combine synchrotron with TM, but now what we can do is the usual, working not in situ but ex situ. Do first analyzing the material, then performing the reaction, and then taking the material after the reaction and analyzing this. This is what we usually did without these new sample holders. So you are analyzing the material of reference before, and then in this case is after cycling, you see that the material, it has a lot of precipitates. In this case, it was bismuth vanadiate, So the bismuth was segregated after the process. So this is something that you can do ex situ, before and after the reaction. But you can also move and do it in situ. In this case, what we did is applying a gas inside the microscope. So we wanted to do methanation inside this microscope. And the idea was, in 2021, we could publish this paper in which we were theoretizing that the mechanism, in fact, we were applying ceria, which is the base substrate, and then nickel nanoparticles, which have nice plasmonic properties. And under illumination, what we were doing is looking that when you were applying hydrogen together with CO2, you were getting methane at the end of the reaction. But the thing, or we were theoretizing, that the CO2 was reduced next to the nanoparticles because the plasmons could hit, under illumination, the plasmons from the metal nanoparticle could hit the surroundings of the nanoparticle, and these parts were really reduced with the hydrogen, but also the spillover of hydrogen from here. With the reduction, you could absorb the CO2 molecule, and then with the spillover of hydrogen, you could create the methane with the CO2 that is already reduced. But in this case, what we could do is doing it directly in the microscope. And the nice thing is that when you were applying hydrogen with the CO2, you could see here by heating, because here we couldn't illuminate the sample. So what we were doing is, instead of illuminating, we were heating the sample at similar temperature of what we thought it was the one provoked by the plasmons. And in this case, what you see is that the reduction of the ceria is exactly around the parts where the nanoparticle it is. So in these places is where the reduction, because you can control the oxidation state of ceria, for example, by doing electron energy loss spectroscopy. You see the difference of the peaks, and you can determine and map the oxidation state of your material. And like this, we could see the process in situ. So it's another way to demonstrate or to prove that your reaction is exactly what you were proposing. So at the end, I don't know if I have 5 more minutes, or if you are tired, I can just finish here. But this is another part in which we have collaborated with groups here in ICMM. So with Ramon, for example, and looking for Majorana, or looking for quantum materials. And this, in the past, was used for electronics, optoelectronics, photonics even. But these nice nanowires now, and these nanowire networks that are hybrid, you are combining semiconductors with superconductors. There's a lot of theory around, but then you can go for Majorana states, ideally, or at least you can try, or you can go to these 2 electron gases or 2-dimensional whole gas systems. And in this case, it's also very important, the part of microscopy, but for the same reason. Because analyzing your material, you can finally determine the structure and get and know what is going on here. So I will just be fast, but in this case, imagine you have a core of a nanowire. This is a kind of cross-section. So this is the core. When the core is cylindrical, in the cross-section is like a closed sphere, and you are growing the shell on top, you see that the shell needs to adapt to the core. And in the case of this shell, when it's covering the core, you see that this is a kind of rotation map in which you see that at both sides of the shell, you have a ±2 degrees rotation. So the shell tries to adapt, and adapts by flexing a little bit. So this is a kind of elastic relaxation, but also you see a lot of misfit dislocations on the side, which is a kind of plastic relaxation. So there is a combination mechanism between plastic and elastic relaxation that at the end makes the material to grow perfectly, let's say, epitaxial, but relaxed. So the material creates defects, and it's flexing, but let's say the cell parameter is exactly the same in the whole shell. So the material, it's not strained, it's relaxed, but it has to somehow deform. But what happened here? When you are using a flat surface instead of circular, what you have is that there's no rotation, so it's perfectly flat. This is another way to relax your material. It's just flat, and it can be grown like this. But if we take into account the polarity of this material, you see that your material is composed of these dumbbells. Dumbbells because you have the cation and the anion. So what is going on when these dumbbells are flexing? So it's that you are creating a potential in between them. You are creating an electric field, which is maybe not good for your material. But this is something that you don't know if you cannot see. So at the end, you are creating this potential barrier here, and you can always take your material, relax it, and see that, yes, this is what happens. It's trying to flex on both sides, and then, again, it's more or less comparable with the real. So that is the model, but this is the real case that you are getting. And then finally, you can calculate the potential, this electromagnetic barrier in the middle that is created by this flexing of the dipoles exactly in the middle part. And this is what I showed you before. You can go further and calculate the band gap here and see that the strain at the interface, which is visualized here in this type of image, this is a special type of mode in STM that is showing you which are the parts that are more strained. You see that the material is more or less homogeneous, but at the interface, the strain is super high. And this is what you can see here. Exactly at the interface, you have a transition of the band gap from direct to indirect. So there is a small decrease on the band gap at the interface, but this is not the main point. The main point is that it goes from direct to indirect band gap, which is a really good result. And now what we are doing is getting this model here that we were using, and the next step that we are working on now is to automatize this. So now, with machine learning, what we do is that all this is automatic, because Mark, in order to get this map, he was like half a year simulating many things, because every single pixel has to be simulated in the model in order to extract all the noise that you get. I mean, not the noise, but you have a lot of parasitic radiation like Cherenkov, etc. And you need to simulate everything in order to extract it and get the nice image that you have here. But now this can be all automated and do it super quick. And this is the part that I'm telling you about. This is the way to analyze your data by automating using convolutional neural networks or machine learning, depending on the different parts. And we are trying different types of clustering algorithms in order to do segmentation and identify the different parts of our materials. These are nanowires, and these are core shells in some cases with the substrate. And we are trying to identify this automatically and also trying to denoise the patterns, the fast Fourier transform patterns or the diffraction patterns in order to identify every spot. And then now, for example, what we can do is all this, you put the image and automatically you get the identification of the structure you have there, even the orientation, etc. If there is a strain, you can map it, and this is all done automatically. So what you only need to do is go into the microscope, take the pictures, put it in the microscope, and you get all the information about your sample, which was taking many, many weeks before for all the members of the group. So this is not the group exactly, but this is all the people that is providing all these possibilities in ALBA. So some of them are part of the group, but also there is the electron microscopy unit, which is taking care of all the users that will attend there and will want to get the results. So I think that is all. Thank you very much for your attention.
Coming and for this beautiful seminar. Yeah, you have opened a lot of expectations about the project. So questions or comments?
Really nice talk, thank you. I was wondering about the MOS2. I mean, these grain boundaries, they're very reactive. And well, I do simulation, so disclaimer. I was wondering how much this imaging could affect the coordination and
a lot.
Yeah.
Just on purpose, I don't know if you remember, there were some images there where the atoms were moving. Could you, I don't know if you noticed. Yes. Exactly. So that's the point. When you are in the microscope, either you work at really, really low voltage, monochromating and doing all your best in order to not affect the sample, or you get what I was showing. So the atoms are moving. So you are reconstructing every one of the grain boundaries, and at the end, you don't really know what you are getting. So the only way to do it is focusing your sample far away from the grain boundary. We were lucky because there were grain boundaries everywhere. So the size of the grains were 5 nanometers, 5 to 10 nanometers. So in one picture, we took many of them. But the idea is going to another site, focus, get the corrections, etc., and then moving to the place where you want to take the picture and get the first one. Because in the videos, if you are there for several seconds, what you see is that there is a reconstruction. And then you are not really, merging the grains, but you really are changing completely the type of boundary you have. So the only way is get the first picture, and that's all. And it's steady for a few seconds. After that, everything moves.
More comments? Questions? If I understood correctly, if you want to apply for this new stuff, you have one single entry point. I mean, for if you want to go to the to the microscope and then to the synchrotron, is the same proposal or is differently?
No, they opened the proposals for ALBA are on one side, and then the proposals for the GEMCA. But once you are applying, you can also add the other one, or at least this is what we are trying to do. I think it already worked. So in your proposal, you can select the beamlines plus adding the microscope and the FIP. So if you need FIP and you need the microscopes, you can add them. Okay. That's the idea. So that you don't need to, if your experiment wants to do everything, it's better to apply together.
To apply together in one single project.
Yes.
And what about this sample environment, the cells? They are stable, they are good enough, they are quite homemade? Or
No, they are commercial.
They are commercial.
So that is, in order to start, with the project, we bought the commercial ones. And then with eDream, this European network, we are working on the designed one by ourselves. So we have now several projects at the European level for the design of new infrastructure, things that are not commercial. And in the case, for example, my group is in charge of a photocatalysis cell, because the ones that are commercial are not including yet, companies are working on that, but they are not yet commercial, the part of illumination, and this is key. Because the experiment I was showing you, you can say, okay, you are not illuminating, so maybe the reaction is not exactly the same, and it's true, it's not exactly the same, but, sorry, but yes. But the idea is this, developing also new types of cells, and with this in mind, what we are trying are cells that are good for the microscope and at the same time good for the synchrotron, which the commercial ones are not really taking this into account.
Yeah, because as you said at the beginning, there is a big difference in the spot size.
There is.
So the cell is the same, or can you work with that?
What we are doing now is adapting the beam lines to focus at the area that the TM cell allows you. So the TM cells have around 30 microns, the window. If it is smaller, it's better because they are more stable. So when bigger it is, you can break them and imagine the liquid inside the microscope.
Yeah,
it's a disaster. It's a disaster. But yes, so what we are trying to do is, in the ones that we are designing, we are thinking about different types of materials to get larger cells to be better for the synchrotron, which are not yet commercial. And that's the idea, to play around. But all the commercial companies are really keen to collaborate. So when we are telling them, okay, but we want to do synchrotron plus this, as we are not alone, we do it with many other synchrotrons, they are really keen to collaborate, because it's not just for one, it's for many other users and facilities.
More questions, comments?
The nanoreactors, that's in liquids?
Well, there is one in liquid, one in gas and vapor, Because in the gas one, you can add vapor as well, different
No,
types.
I meant the results that you were showing with this.
No, that is gas.
single
That is
atom.
gas. It's not electrocatalysis. It's catalysis.
Okay.
Yeah, that was with gas,
Okay.
Hmm.
And
mixing CO2 and hydrogen.
Okay. So and perhaps what would be the integration of scanning probe microscopy methods within this joint facility? I mean, how how scanning probe? I mean, how do you plan that? Yeah, to integrate. I mean, what would be the synergy? What would be the?
So with the TM, we are a bit separated in this case. So the synergy is with the beamlines, because they have already experience with the beamlines. So there are already these vacuum chambers that they are using in order to do STM. Aitor Mugarza is doing that for many years now. And they can move their chamber to the synchrotron and then measure with X-rays. So in their case, they are planning this, and we are planning similar things. But by now, we didn't talk yet about doing synergy between SPM and electron microscopy with the same sample holder, because they are totally different techniques. It's quite different. So because the problem is that they need to reach the surface.
Exactly.
And we cannot let them reach the surface, because if they reach the surface, they break our window. So that's the problem. And there are some commercial holders where you have the tip of an AFM, but then they are not covered. They are not yet, I mean, they do not have windows in order to introduce gas or liquid. They are in vacuum only. So still, there are many things that will be done maybe in the future, but this is not yet, we are not at that point yet.
Because the first two examples you showed, I mean, there I really see how, I mean, how SPM in general, let's say AFM or SPM, could kind of complement both from the chemical characterization and from, say, a less evasive way to characterize this reactor.
Totally. Then what you need is a perfect clean surface, etc. But yes, you can do it in another way. The same sample, you can take out the grid and put it in the AFM or SPM or STM and measure it there. That's another option. The thing is that at the moment we are working in different type of materials, but that's a possibility. And once we are all there, I mean, we have a lot of communication, because the project, we are all day talking on how to do it. So yes, but at the moment, we didn't think yet about combining SPMs with TMs yet. But once it's there, yeah, why not?
Hi, this is a practical question regarding how the projects are organized with regards to sample preparation. So for the TM, what is the idea? You have your samples already prepared and you have had a look in a microscope somewhere, and then you apply for bin time to do something special, or can you go with a sample you think is marvelous and try to get the sample preparation in situ?
It can be done. So as I showed you, we have a sample preparation lab in which, when you apply for the proposal, you can ask also for time in the sample lab. So what we offer now, it's the FIP, which is the quickest one. It's not good for all the samples, but for many semiconductors and, I don't know, electrodes, it's really, really good. Sometimes you can just prepare, if you have powders of nanoparticles, it's super easy. It's just depositing. You can do it there or here, I don't know. What we ask is, please check before the sample in a SEM at least, or in a normal TM, in order to know if it's not contaminating, because the problem is that it's super, I mean, for example, the number of proposals we got last year for the first call, it was more than double that what we could get, so it was amazing. And this time I think it will be even more. So the thing is, if you go there and your samples don't work, because the easiest is that you put the beam and you contaminate everything. And it happens, it can happen a lot. And then you are missing some time that someone else could use. So what we are asking is, if there is a way to check the sample before, even better. Because this is what the committee, there is a technical committee that is checking every proposal before sending it to the scientific committee, and they are the ones that will suggest you what to do or what is the best, and even help you. Because you can always get some time, if you don't have a microscope, you can always do it. We have a small microscope also in ICN2, so there is a possibility to ask for a few hours in that one, check that everything is going okay, and the day after you go to the one in ALBA. And then you, at least, you are sure, you are never sure 100%, but at least you know that the thing will work. But you will have always someone that will help you with your ideas. So it's not that you go there and you will be alone. No, there will be someone that will stay with you and that will, if you are not a microscopist, if you want to do it alone, we don't have auto service yet. I mean, we have auto service for the people that is always there. But if you, for example, want to do microscopy and you know that regularly will be going, that's another option to get experience there and learn how to use it.
And apart from FIB, you also have the conventional ion milling system.
We have ion milling. We have different diamond saws with a wire saw, the regular with the, we have everything you need, the tripod if you want, or the automatic lapping films with diamond. So we have everything. But since we had the FIB, nobody's using that. The FIB really works. Super, and it has a cooling system, the FIB. So for samples that can be beam sensitive, there is the way you can cool the system and then cut. So it's minimizing the damage.
Okay. Any other question or comment? If not,
Sí.